but I don't have time to do that right now. And our classes I did. So section 3.1 functions. This again should be review because all of this is review for the most part. What we're going to focus on is determine whether a relation represents a function, using function notation, find the value of a function, find the difference quotient of a function, aka the slope, for the most part at a point, find the domain of a function, and form the sum and difference product and quotient of two functions. Again, this one area is roughly all of unit 1 of Algebra 2. So this one section, almost the entire unit 1 of Algebra 2. All right, so we talked about a relation. A relation is a correspondence between two sets, a set X, called the domain, and a set Y, called your range. Yes? All right. So when you have a relation, that means you have something being input and something being given as an output. So you have an input and a output, okay? The relation is what takes place in the middle, and boop, there's your output. Cool? Sounds familiar still? So if you look on my vocabulary wall, I have the idea of a vending machine. A vending machine is the best example of a input-output situation, right? You input a code, and it does some thinking, and then bam, your output, right? Okay. So questions about that? Okay. Because we say that Y depends on X, that's why Y is our dependent variable and X is our independent variable. Okay. So a relationship can be expressed verbally. So I could describe something to you numerically, as a set of ordered pair, graphically, and as a mapping. All these sound familiar? Okay. And so, for example, here's a verbal representation of a ordered pair. So the average retail price of gasoline in the US has changed over the years. In 2010, the average cost of 1 gallon of gasoline was $2.78. In 2012, it cost $3.62. In 2014, it cost $3.36. In 2016, it cost $2.14. And then 2018, we started going back up and it was $2.72. Okay. So if I wanted to represent this as any other form, I could, but this is a verbal representation of a relation. And that's because every year has a corresponding value, right? Okay. So what we have here is that we should be able to describe what's taking place. So what would be the domain and range of this relation? And you should be able to write it as an ordered pair, as a mapping, and as a graph. Are these 4 things you feel confident that you're able to do? Describe the domain and range, write it as an ordered pair, create a mapping, and create a graph. See? Yes. Yes. So the mapping is the 2 circles in numerical order, and then you draw the lines to connect them. Okay. All right. So let's just go through this quickly. Is that cool? Let me know if I'm going too fast. So first thing is establishing the domain and the range. So the domain would be the years, the range would be the prices. Simple enough. Okay. If we want to be mathematically correct, we would write the domain and range both in numerical order from least to greatest. But for the sake of just listing, as long as you understand that it's just which is your dependent and which is your independent, then you're good to go. Okay. If I wanted to write it as an ordered pair, it would be my year, comma, my price, and bam, I have my ordered pair, correct? All right, still going, creating the mapping. So I create the mapping. Notice for the mapping, my dependent and my independent variable are both in decreasing order. And then I draw the lines to connect where they correspond. Mapping done. Questions? All right, lastly, the graph is just literally plotting the points to see if there's some type of correlation that I can analyze from the graph. As I can see here, there's a fluctuation, so I can't say whether it's linear or quadratic. It looks slightly cubic, but not, yeah, cube-root. Cube-root? Yeah, cube-root. Little, actually looks more like a sine graph right now, if I'm gonna be honest, but we're not there yet. So that's it, easy enough. That was 1 week of Algebra 2, by the way, for the most part. So determine whether a relation represents a function, okay? Definition of function. is that for every the x into y, there's only one x being utilized, right? So your x isn't being repeated. And that's why I said think about a vending machine. A vending machine is a great example of a function. When you type in one code, it's going to give you one output, right? Now, could you have two things in the same slot? Yes, but their codes are going to be different. So my y's can repeat, but my x's do not, right? That's what makes it a function. So as a mapping, that means from one domain value to the other, there's only one arrow going from each one. So notice here, there's only one arrow. So this would be considered a function, right? So from each domain, there's only one arrow. And then the range can repeat. So I can be going to the same y, but I'm only coming from a different x. Okay. So for this mapping, is this a function? So we have here puppy tacos and their prices. And it is a domain. It is a function, right? Because if I look at my domain, yeah, some of the items cost the same price, but the items don't cost more than one price. Does that make sense? Okay. All right. So therefore, we would call this a function. All right, let's look at another example. What about this? Is this a function? Is this relation representing a function? It is, because our domain values are Gabriella, Oscar, Steve, and Amanda, and our range values are correspondingly individual as well. So this is a function, okay? All right, is this a function? No, why is it not? Aaron goes to two places somehow. How does Aaron go to both colleges? Aaron can't go to both colleges. Okay, so this is a relation, and Aaron's going to make a choice between Princeton and Duke. Okay, easy enough. Again, please let me know if I'm going too fast. So the same concept when you're doing ordered pairs. So ordered pairs, you're analyzing the x value. So the x in the ordered pair is what you're looking at. And if the x in the ordered pair does not repeat, then it is a function. So if we look here, we have 1, 5, 3, 9, 5, 1, 9, 2. Is this a function? And yes, it is. It is a function because my domain values do not repeat and there's only one corresponding x value. Cool? Okay, keep it pushing. Is this a function? You're so smart. Good job. And is this a function? No. And why is it not? -5 repeats. Okay, so therefore this is not a function. It's just a relation. Good. All right. Again, let me know if I'm moving too fast. Okay. Next, we're going to talk about determining whether an equation is a function. And so here we have y equals 3x plus 7. So with 3x plus 7, we know that for every x value, I'm going to have a single output, right? So for each one of these x values, it's going to give its own output. And because of that, that makes this a function. Okay, x equals 1 is only going to be 10. X equals -3 is only going to be -2. Does that make sense? So for each one, it's just going to have its own. And to be more specific, we also know that this is simply a linear function. And it's called a linear function. So therefore, we know it is a function, not just a relation. Okay, what about this? We have 6x plus 3y squared equals 2. Would this be considered a function? No. Why is it not? Exactly. Your y is going to be squared. So when you isolate the y, so when I subtract the 6x, then divide by the 3, I'm going to take the square root. And when you take the square root, what happens? You get a plus or minus, right? So that means that your x values are going to repeat because it's going to have a positive output and a negative output. Does that make sense? So therefore, this is not a function. Okay. And the only way that this would become a function is if you set restrictions, but until then, it is not a function. Okay. And notice that I had to state that in order for this to be even considered as a function, I had to analyze the restriction. So review of analyzing restrictions. When you have a square root function, you have to define the restriction. It has to be greater than or equal to 0, right? Because it has to be positive. So when I'm finding this restriction, I'm going to multiply. I'm going to subtract 2/3 from both sides. I'm left with negative 2x is greater than or equal to negative 2/3. Then I'm going to divide negative 2. When you divide with an absolute value, what happens? It flips the sign, right? And so I divide, and dividing means multiply by the reciprocal. And that leaves me with 1/3, which is why, in order for this even to be considered, I have to have that restriction. That x has to be greater than, and it should be, or equal to, because you can have 0. 1/3. Okay. But that plus or minus, that's your key thing right here. If this is part of your function, then it's not a function. Okay. All right. Function notation. Function notation is basically the fancy way of saying y, right? F of x. That is function notation. Function notation is our way of symbolically saying we're going to substitute in a value. Okay. So we're substituting in a value. So for example, if I have f of x equals 2x minus 5, and then I have f of 1, that means that I substituted in 1 for x, and my output was -3. So this came from substituting in 1 for x. That's what function notation means, right? Okay, and this came from substituting in 3 for x. And that's what my output is. Okay, so function notation is just saying, it's a notation saying I substituted in a value for x, and this was the output. So this is the function notation. We made a little booklet. Remember, tiny booklet, little flip book. All right. So again, you have an input, which is your x. It goes through some thinking, and then it comes out as your output, which is your y, which all dressed up is f of x. Okay. The restrictions on this input and output are: it accepts only numbers from the domain of the function, so it has to be a value that would give you a real solution. And for each input, there is exactly one output. Okay. With function notation, the x variable is called our independent variable. So your independent variable, and it comes from your domain. The variable y is called your dependent variable, and it produces your range. Okay. In some more fancy books, you may hear that the independent variable is called the argument of the function. Just throwing that out there. If you plan on taking more advanced math, you may hear it called as the argument of the function. All right, so brain check. So here, there's a series of things that you're going to be doing. So we're going to go through these 8 scenarios of using function notation. Okay, we're going to be using the function f of x equals 2x squared minus 5x for each one of these. Okay, so we're using f of x equals 2x squared minus 5x to evaluate each one of these together. Cool. All right, so we're going to be doing all 8 of these. We're going to do a little bit at a time. So to start off with A, if it says f of 2, that means I'm substituting 2 for x, correct? Because function notation means substitution of x. So instead of x, wherever there's an x, I'm replacing it with a 2. Agreed? Okay. So everywhere there's an x, I put a 2. And then I evaluate. That's the basis of function notation. Are we good with the basis? Yeah. All right. Now we're going to take it up a notch. So if you look at B here, it says f of x plus f of 2. So we're going to have the function unchanged plus the value of f of 2. Do we see that? Okay. So what that means is we have the unchanged function plus the value that we got for f of 2. And the value that we got for f of 2 was -2. And all you're doing here is combining like terms. And is there any like terms for me to combine? Nope. So then therefore I'm done. So this would be my final answer. Because there's no like terms to be combined. Okay. On C, it said we are going to do 2f of x. I don't know why that line happened, but 2f of x means that I'm multiplying every term in f of x by 2, right? So I'm multiplying every term by 2. And that's literally because I'm distributing the 2 to each coefficient. So I distribute to each coefficient. And I have 4x squared minus 2x. So I can multiply with function notation. Do we see that? So we added with function notation. Now we multiply with function notation. Cool. All right. The next one, we are substituting negative x in. So we're doing f of negative x. So instead of my x being positive, it now becomes a negative, and we make that change to the function. So we substitute in. This doesn't affect anything because a negative times a negative is a positive, but this has a change. So instead of it being -5, it now becomes a +5, and this becomes my final answer. So do we see how changing the x to a negative slightly affects the problem? Okay. Next, we're going to change the outside of the function. So this time we have -f of x. Because I have -f of x, that means I'm distributing the negative to the coefficients. Not to the variable, but to the coefficient. So I end up with 2 times -1, which is -2. And -2 times -5 makes a +5. Do you see the difference between D and E? One was distributed to the variable, and then the other was distributed to the coefficient. Yes. Okay. Yeah. On D? On B? Because our solution for f of 2 was what? Go back. For f of 2, we got what? -2. So we already know what f of 2 is. It equals -2. And then when we plug it in, we're just substituting in what we already know what the output is for f of 2. Okay. So again, on E, unlike D, we distribute to the coefficients, and that's how it changes. Still good with function notation? All right. F. So this time it says substitute 2x for x. So we have f of 2x. So that means for each one of my x values, I'm doubling them in size, right? So wherever x is, it becomes 2x. So notice here, it becomes 2 squared, which makes 4, and then 4 times 2 makes 8. So we went from here, and then 2 times 4 to here. Okay, now we have -5 times 2, and that gives us -10. Nothing else needs to change. So we end up with -10x. And that's where we stop at. So good? All right. Then we will continue this tomorrow.